to have here, there's amongst us Professor Erik Ghysels, who is the Edward Bernstein Distinguished Professor of Economics and Professor of Finance at the University of North Carolina. University of North Carolina. He's a world expert in time series econometrics. He's the editor of the Journal of Financial Econometrics. He was a Duisenberg Fellow at the European Central Bank, and he is an absolute extremely well-known person in the field of econometrics. So it's an enormous pleasure for us to have you amongst us here. And Professor Ghysels, the floor is yours.
Thank you. Thank you for the nice introduction. I assume that everybody can hear me and see my slides. Thanks for the kind invitation. It's a really great pleasure to be part of this conference at the Fields Institute. I've changed a little bit plans. I'm going to talk about a number of papers, not just one, the one that was announced on the program. It's going to be a little bit of a journey. Namely, I'm going to start with a brand new hot from the press paper with Jack Morgan on classical shadow non-parametric bootstrap. Then I'll transit to quantum quasi-maximum likelihood estimation. I'll be rather brief on that. That's kind of a transition between the first and the third. The third is the paper that was announced on the program on quantum and quantum-inspired maximum likelihood estimation and filtering for stochastic volatility models. I have about 100 slides, but that's not going to be feasible. We have about 50 minutes from what I understand. I'll keep an eye on time. So I will kind of skip parts. So let me start with the first topic, which is the one on classical shadows. So a recent paper by Wang, Kong, and Preskill presented an efficient method for constructing an approximate classical description of a quantum state using very few measurements of the states. So this was basically saying that if you have, you want to predict m different functions, m capital M different functions, it involves log m measurements to describe accurately those m different functions. So you're not really trying to do full state tomography. You're just trying to figure out a number of interesting functions. Now the motto, and they call that classical shadows, this procedure. The motto of classical shadows is to measure now, meaning that you just compute these classical shadows and their classical data once you do these measurements. And then you ask questions later once you have collected all this classical data. What our research suggests is to measure now and ask many more questions with resampling. That's going to be the theme of the first paper. So what we're talking about is something as non-parametric bootstrap. Bootstrap as a statistical procedure is a resampling method. It's one of many resampling methods that uses is used to assess kind of the small sample distribution of any particular statistic by repeated sampling with replacement from the observed data. So you kind of treat your observed data as if it were the population, and you randomly select sample sizes equal to the ones that you have to construct statistics over and over again. This is an idea that dates back to Brad Efron's work, and it allows one to approximate the sampling distribution of virtually any statistic without very strong assumptions. I mean, there are some assumptions to be made, which I won't get into, but they're rather mild, actually. So in practice, a large number of bootstrap samples, each of the size of the original data set, are drawn and the statistic of interest is computed for each. And so typically you got B, the number of bootstrap samples, equal to, say, something like 10,000. So if your original data set is a classical shadow of with a sample size of 100 or 1,000 or 2,000, you create 10,000 copies of that original sample by randomly drawing from it with replacement. This generates an empirical distribution that can be used for all sorts of things, and that is what we're sort of will be doing, and that's about asking measure now and asking many more questions thanks to the resampling. So one can think of actually classical shadows as a Monte Carlo experiment involving random draws of unitary operators. I will get into that more explicitly later. And Bootstrap is also a Monte Carlo experiment applied to a given data set. So, therefore, doing a Monte Carlo of a Monte Carlo, if you like, is itself a Monte Carlo. And so instead of sort of having one classical shadow sample of size, and what we have is 10,000 samples of size, and with the same efforts of what you did in order to get the 1,000, the original classical shadow sample. So it's important to stress here that we're a little bit dealing with different disciplines. The term bootstrap has been used in computer science literature, and it has many different meanings in the computer science literature. So I wanted to emphasize that what we're talking about is I'll call it the statistical bootstrap, and it's one of many resampling methods in statistics. The jackknife is another one. Cross-validation is also a very popular one. So this is not what computer science people think about as bootstrapping, which relates to a number of things about operating systems, compilers, etc. So to the best of our knowledge, the use of this statistical non-parametric bootstrap is novel, and it opens up a lot of interesting directions, actually. A few words about classical shadows. So you have an n-qubit system and a quantum state that you don't know of dimension to the power n. The unknown quantum state rho is subjected to n randomly independently chosen unitary operators that are used to measure the unknown quantum state, and those measurements are performed in the computational basis. And then these unitary operators rather, they are drawn, as I said, randomly from a tomographically complete set. The general idea is known as a Haar random unitaries. This could be poly operators and tensor products of poly operators, and Huang, Kong, and Preskill call that local ones because you kind of apply a randomly chosen poly operator for each qubit, and then you take a tensor product, or more what they call global ones are Clifford ones. But there's anything in between that is also possible with certain regularity restrictions. So you draw these classical shadows from basically selecting randomly these unitary operators from whatever class you've picked. And you can sort of think about, if you do this over many unitaries and across outcomes, that this is kind of a quantum channel. You can think about that. And inverting that quantum channel yields you kind of an estimate, a classical snapshot of the unknown quantum state. And you do that, you know, a number of times, say 1,000 or whatever you pick as the sample size of your classical shadows. You get therefore a sample, and your expectation value of that sample is the true unknown quantum state. So you can sort of think about estimators based on that. Classical shadows are particularly suited for predicting linear functions, although they're not limited to that. And so you can think about observables of size m, which is what we talked about on the first slide. And you kind of look at these different observables that you select. Now, if there is in that classical shadow paper discussion about what is the distribution of that estimator that you get, and it depends on something that is known as the shadow norm, and that itself depends on the type of measurement, whether the unitary operators, the higher measure that you have selected. So there is a variance that comes out of it that is an asymptotic argument, actually, and we'll see that's going to be problematic. We do this for a toy example. This is only displaying 4 qubits, but it's a 10-qubit system that we look at that involves a number of rotations. And we have a total of 27 observables that we construct from this circuit. And here is, for the first observable, what you would expect to be the distribution of that random classical sample, classical shadow, based on the Gaussian distribution. By the way, this MOM stands for the median of mean estimators. What Huang et al. Do is that they split up the sample in subsamples. They estimate the mean over these subsamples and then compute the median. You don't necessarily have to do that, but that's sort of what they do. On what you see here is a Gaussian density, meaning that you looked at that you used the mean of your observable one through those, in this case, 1,000 classical shadows. And you can see that the true expectation value is the vertical green line. You can see that there is a small sample bias because that distribution is shifted to the left. And there's going to be also an issue with that Gaussian approximation not to be particularly good. So that means that we're going to think about Bootstrap, because one of the things that Bootstrap does is it allows you to actually estimate the small sample distribution, not using the asymptotic approximation. We're indeed expecting a non-Gaussian behavior, especially in small samples, heavy-tailed and unsymmetric due to the structure of this classical shadow measurement process and this inversion map from the quantum channel. In some special settings, Gaussian-like behavior emerges as asymptotically through a central limit theorem that's been shown for a number of observables, such as those local Pauli unitaries. So the Bootstrap procedure is, once you have your classical shadow, you construct an empirical distribution of it, which is just if you think about it, it puts 1 over n, where n is the sample size of the classical shadow. It puts a mass 1 over n to each of the observed data, and then you randomly draw with replacement. That is to say, when you draw a classical shadow observation, you put it back after drawing it, and so that can potentially be repeated in terms of draws. You do this for capital B Bootstrap samples. Each of them are of size n, and that gives you here the row hats for bootstrap B, small b, for b equal to 1 to capital B. So you got, say, 10,000 classical shadows that you randomly selected from your original classical shadow sample. And that's sort of now, in some sense, supercharging your original classical shadow. You only do this effort once to create this classical shadow sample, and then you use classical bootstrap methods, statistical bootstrap methods, to just supercharge that original classical shadow. So that allows you to look at a statistic for each of the bootstrap samples, say, for instance, the median of means or something else that you're interested in. And so you got now capital B of those mediums of means. And that gives you an empirical distribution that you can start looking at. And you can compute, say, standard errors or whatever you want. So this is what happens with a bootstrap of 1,000 for a original classical shadow sample of 1,000. We'll look at what happens when you increase the sample size. You would expect that small sample bias is going to disappear, and it does, as we mentioned earlier in some cases. But what's more important is that this distribution, so what you have here is a histogram. That's the histogram. And then there is a smoothed kernel density estimator. That's the blue solid line that goes through it. And what you observe, of course, is that that Gaussian distribution that you have from looking at the average of the classical shadow and the standard error variance that comes out of it from the expansion that you have with the shadow norm isn't particularly a good description, particularly not for the tail behavior as we expect. And we also see an asymmetric distribution in this particular case. Also, Huang, Kung, and Preskill, they derive bounds, risk bounds on the error. I will not go through the math on this, but they have, and as you expect, these are, again, sort of asymptotic derivations. And these bounds are particularly not particularly tight. As you can see from this, this is the 95% risk bound that you get from their computations. This is the 50% risk bound. And these box plots are for classical shadows of size 500,000 up all to 2,500. This is the bootstrap distribution for the 500, for the 1,000, etc. You can see that this thing is shifting and shrinking. That means that the small sample bias that we highlighted earlier is getting smaller. But obviously, the percentiles from this from this bootstrap distribution are much tighter than what you would expect from the asymptotics. And so there are better descriptions of what's really going on in terms of your classical shadows. This brings up a question that I think is kind of interesting. I mean, most of this conference and a lot of the literature is about how quantum computing is kind of being used in solving finance problems. This actually is kind of traffic in the other direction. Namely, what I'm basically alluding to is the fact that we have in finance we have thought a lot about measures of how to manage risk, in particular in portfolios, and bad outcomes of particular portfolio outcome returns. And so you can sort of think about this classical shadows as a random variable that has a distribution, and it has a multivariate distribution. So far, I only talked about the one-dimensional first observable, but we have, in some sense here, a 27-dimensional random variable. And we're often interested in functions of that. And by the way, I'm talking about expectation values, but you know, in the classical shadow paper that I've been talking about, they give examples such as fidelity. So what's the fidelity of my system, of my quantum circuit? And you don't necessarily want to just focus on what the expectation value is of that. You want to really look at what's the worst outcome. And so we have a lot of tools in finance, such as value at risk, expect shortfall, to sort of assess tail behavior. And as you saw, the bootstrap is kind of a way to get at that tail behavior. And the asymptotics is kind of not a good guidance on that. And so there's a lot to be done here. It kind of opens up an interesting research project, actually. Moving on to, so that's sort of the end of classical shadows, non-parametric bootstrap. So I'm going to transition to quasi-maximum likelihood estimation. As it transitions and gets me to the stochastic volatility paper that I'll get to. So in physics, the data is typically experimental. And notions of model specification errors are rarely considered. In econometrics, we have a long tradition. We don't really have experimental data. We do have a little bit, but it's not really. The bulk of the data is non-experimental. It just, we get data from stock markets or financial markets in general. It is what it is. It's not, it hasn't been experimentally designed. So we are used to think about what's known as quasi-maximum likelihood estimation, meaning that you're looking at a likelihood function, but you know it's not necessarily the true likelihood function because it's either unknown or it's difficult to compute. And so we know a lot about this. The original work was done by Hal White in 1984. It's an econometric paper. And since then, there's been a lot of work in quasi-maximum likelihood. Now, there is a well-established asymptotic theory, notably Lucien Lecomte's local asymptotic theory, normality theory, LAN as it's called. The quantum version of it has been studied quite extensively. This is for correctly specified models, but it's not for when there are specification errors, when you know that you don't have necessarily the true model. And so what's interesting in that literature is that what they show is that that under certain regularity conditions, a finite dimensional quantum statistical model converges in distribution to a quantum Gaussian shift model. That's sort of the equivalence in classical statistics of the exponential location scale family kind of results that we kind of have that as the central object actually in most of the quasi-maximum likelihood literature. So suppose you do have a quantum an estimator that is for a quantum state. So the quantum state is parameterized, which is not unusual, by a smaller dimensional vector theta. That quantum state is written as sigma of theta because it approximates the true unknown quantum states rho, which is not necessarily the right model. So you have an approximation in your model. And for IID samples, the asymptotic distribution of this estimator is not quite the usual Fisher information result that you get because your likelihood function is not correctly specified. You get a sandwich formula that involves the outer product of scores and the Hessian. It collapses to the standard correctly specified maximum likelihood. When the model is correctly specified, these A and B's match each other so that you get the usual formula. Now, there is a paper in a Journal of Mathematical Physics that looks at this problem, that derives this distribution. There's not really a full sketch of a full proof in it, but it has that asymptotic distribution in the context of quantum. Now, the thing about quantum is that I'm going to skip this slide. The thing about quantum, of course, is that you're talking about non-cumulative statistics. And even in the correctly specified setting, the metric that you use is not necessarily, there's sort of ambiguity about it. There's one that is known as the symmetrical logarithmic derivative. And the other one is what is called the BKM, which is a metric that relates to the surface of the relative entropy. And it's not so clear which one metric to use for misspecified models. And the BKM metric, I think, is more appropriate, but I'm still kind of working on that. But if you want to think about parametric models and that are potentially misspecified, and you want to think about their small sample distribution, which is what we did with the classical shadows, then we're going to have to think about what's known as a parametric bootstrap. And that needs still to be worked out. So this is work in progress. That parametric bootstrap will probably, I'm leaning towards the BKM metric to sort of develop it. And there's also interesting work on non-parametric bounds by Spokorny, which you will see that's not deriving the actual distribution of the estimator for theta of your quantum state, of your approximate quantum state, but instead finding bounds on it that are valid for finite samples. And we'll get back to that in when we talk about stochastic volatility models. I have about 22 minutes, I think.
Yeah. We have a coffee break after that, but we can also go a little bit into the coffee break, I would say.
Sure.
Please continue. Please continue.
Thank you. So all of this, why is because I'm going to have to talk about approximate models when we talk about stochastic volatility models. And so we're going to have to estimate these models with maximum likelihood methods that are not necessarily correctly specified. In fact, we know that they're misspecified for sure. So that's where things are kind of connecting between the three topics of the paper. Three papers, rather, topics. So this is work in progress. Okay. So this is getting to the paper that appeared on the program in terms of title. It's on archive. The first paper will be on archive posted next week, I think. So it's almost finished. All right. So this is a topic that has been on the mind of financial econometricians for a long time. The reason is that we have in mathematical finance a very vast literature on continuous time diffusion models. And now a lot of these models, we sort of like the ones that have exact discretizations, such as the Black-Scholes model, or the geometric Brownian motion, that's the same thing. But those are not really realistic models. The realistic models are the ones that feature time variation and volatility. And so usually what we do is we add a second diffusion that governs the stochastic nature of the time evolution of the volatility. So there's big literature on that because it's used for pricing of derivatives. The problem is that we don't really have exact discretizations for these, except for a few special cases. So this has created a lot of discussion, not only in mathematical finance, but also in financial econometrics on how you estimate these models, because they're so important for not only just equities, but also fixed income assets and the like. So maximum likelihood is challenging. I mean, they're Bayesian sort of Markov chain Monte Carlo methods that are available for it, but they're also having issues with the discretization biases. So, but I'm not going to get into that. That's a separate literature. So I'm going to focus on a continued time diffusion, but everything I'm saying is kind of also true for discrete time stochastic volatility models and many sort of variations of that for its worth. What I'm going to propose are two novel approaches to estimating stochastic volatility diffusions. One, which is called quantum inspired, based on, and it's classical, quantum inspired classical, I meant to say, and it's based on hidden Markov models. And the other one is, the second one is using quantum hidden Markov models. In both cases, the likelihood function is approximate, meaning it's not correctly specified. It's just an approximation only of the true likelihood function. And we also need a filtering algorithm, meaning that not only do we need to estimate the parameters of the model, but we also need to extract, filter the unknown or the latent volatility process, as you will see. The approximations is going to come from the fact that we are going to replace the continuous valued volatility process by a finite set of hidden states. So that makes the computations of the likelihood function easier. And so, but of course, it's only a finite set. Obviously, again, if that finite grid is getting denser, you're getting closer to the latent volatility process, but it's still not the correctly specified model. Quantum hidden Markov models will have a computational speed up, and it's one that comes from the fact that we are going to have a dimensionality reduction, and so that's going to be one of the things that I will be talking about. There are also closed form solutions for the filtering and the likelihood function, so that's kind of appealing, actually. So let me talk about what the sort of approaches that we have. So we have a stochastic volatility diffusion here, which is it's without a drift. You can add a drift. I'm just not going to deal with it. So this is you can think about this as the log price of an asset. So this is the log return. Instantaneous log return is driven by a stochastic process sigma and increments in the Brownian motion. The V is the square of sigma, so this is the standard deviation, if you like. That has itself a diffusion with the drift, volatility drift, and diffusion for the volatility. That also has its own increments in Brownian motion. I'm assuming that those two Brownian motions are independent of each other. Otherwise, the model becomes a little bit more complicated. So this is called in finance leverage effects. But we are assuming that there's a correlation between the two is zero. And it's also independent of the V naught. So we have we're going to have two types of estimation approaches for this stochastic process. One is parametric, where the parameters here pertain to both the drift and the diffusion part of the volatility, and of the V diffusion, the second diffusion. So you care about those parameters, and you also care about filtering the volatility. I sort of use the word volatility interchangeably for V and sigma, that some people get offended by that. They call that variance and that volatility. Sorry for that sort of somewhat casual use of language. But we care about not only the parameters, but also sigma and at each point in time. The non-parametric approach is to say, look, I forget about the second equation. I just care about sigma, and I assume it's a hidden Markov model. And it's non-parametric because I don't really care about estimating the drift and the diffusion part of sigma, of V. And I'm just going to assume it's a Markov process. Now, here is an interesting way to think about it. It's not a very well-known paper by Genoud Catalot, Gentaux, and Laredo. It appeared in Bernoulli in 2000. They used this framework that I will explain shortly to actually look at the mixing conditions, mixing properties, and ergodicity of stochastic volatility models. So what they do is they look at a discretization of this. So this is a discrete time return over some delta time increment. And they write it as a hidden Markov model. But what you need to do is you have to really write it as a join between V bar, which is typically called the integrated volatility. It's the path, the integral over the path of V or over that time increment delta. And V at the end of that time interval, which is sometimes called the spot volatility. You need to have them both jointly here in order to make this a Markov process, because V bar is not a Markov process. The transition kernel for this hidden, what is nice about it is that although you have a stochastic diffusion in continuous time, you suddenly have now a discrete time model. And it's a hidden Markov model. Now, notice again that these V bars and V are continuous valued, but also you don't really know necessarily the transition kernel. That is to say, the transition, what is the dynamics of this Markov process. So in the Genoud Catalot, Gentaux, and Laredo paper, what they do is they don't obviously know how to deal with this. So they can't really do a maximum likelihood estimation or something like that, because there's a missing part, which is the dynamics of the Markov chain. But they do actually derive, since they talk about ergodicity and mixing conditions, they do derive moment-based estimators based on this Markov model. The problem, of course, is that in econometrics, it's kind of known that these moment-based estimators are not particularly well, they don't have really nice sampling properties. So you'd rather do. So what I'm going to do is I'm going to write everything in discrete states. That is to say, I'm going to put my returns into a discrete set of bins, sort of thresholded, maybe with thresholds based on whatever you think about. So that's the discrete states. The finer this grid gets, that doesn't really change the parameter space if we're thinking about parametric specifications. That's true for the case where there is no drift. When you have a drift, though, that's no longer true, but we're looking at a case without drift. Then similarly, we're going to put the V process, both the integrated and the spot, we're going to put them in discrete bins, in discrete approximations. If you actually have a parametric diffusion in mind, and we will talk about an example of that then actually for some of them, you do actually have the transition kernel. And therefore, you know, that parameter vector theta stays the same, regardless of how fine you have the grid. That's not true if you're doing the non-parametric approach, where you just say, I got this process, sigma, and I have spot and integrated for that, discrete states. Then when you increase the grid, you're talking about a transition matrix that increases in dimensions, of course. So what is going to be the quantum advantage here is that you can have a classical hidden Markov model with n squared hidden states. You can mimic that stochastic process, the stochastic features of it, with a quantum hidden Markov model with only n hidden states. So there is a, if you like, a quadratic dimensionality reduction. And of course, that has, if you really think about the n by n transition matrix, if you go from n squared by n squared transition matrix to n by n, that's a huge reduction in the dimension of the parameter space that you have to deal with. This is a parametric way of doing non-parametrics by approximation. So there is the quantum advantage if you implement this quantum hardware, potentially, that we will talk about. So yes, in the interest of time, let me not just, let me skip this on how you connect spot and integrated volatility. That's so the Cox-Ingersoll and Ross process that it's sometimes called, it's a square root process. That's another way to say it. That is for the volatility for V, as you can see, 3 parameters, alpha, beta, and sigma. So those are the ones that drive your V process in continuous time. The nice thing about this particular process is that you've got actually a closed form solution for the transition kernel. So you know how this Markov chain behaves. For any discretization, you can work it out actually if you want to. And you also have the ergodic distribution. It's a gamma distribution, and it's a non-central chi-square for the transition kernel. So that's one case where, for example, you can do a Markov chain with only 3 parameters, and no matter what the discretization is. But that's not typically the case. It's one of the few examples. Anyway, so classical hidden Markov models are defined by 5 entries, if you like, elements. One is the observable process space, the latent process space. So, you know, what kind of observations, in what space does that live? What space does the hidden process live in? The transition kernel, the emission densities, which are given a particular hidden state, what is the probability of observing the observables that you will observe? And then the initial starting point for your stochastic process. I'm just going to call this this huge notation here, this 5-tuple. And what really I care about is the number of hidden states. And this C, superscript C, refers to classical, and L refers to latent, the discretization of the latent process. So so that's a model of that with those features. I suppress all the rest. There is a likelihood function for it. Due to the discrete nature of the outcomes, you have a likelihood function. If there are any sort of econometricians in the room, this is kind of reminiscent of what is known as the Hamilton model, which is used quite a bit, regime switching model in macro, but also some regime switching models have been used in finance literature, except that the Hamilton model only has two regimes, and here you've got a discretization that has multiple regimes. So the rank of a hidden Markov model is something that Anderson came up with. It's based on a generalized infinite Hankel matrix representation of the hidden Markov model. These are outcomes one, the distribution of that, outcome two, all the way to, and then outcomes one and two, pairs of it, and then you keep going. That is an infinite dimensional Hankel matrix. If that matrix has a rank n, then you say that the hidden Markov model has rank n for this, based on this Hankel representation. And a canonical hidden Markov model is the one that has a number of hidden states equal to its rank. You can always have a bigger one, but this is the minimal representation. So now, for quantum hidden Markov models, there is a somewhat similar structure. You got now tensor products of Hilbert spaces. So this is kind of a composite system, because you got a hidden part and a non-hidden part. The latent part is a NQL dimensional tensor product of Hilbert spaces, complex valued. This is the observable NO dimensional. There's a unitar operator that operates on the composites of those two spaces, and there is an emission map that gives you the observed discretization, and then there is an initial state that is again composite of some quantum state for the starting of the hidden part process. And again, I'm going to use a shorthand of MNLQ because I'm only focusing on the dimensionality issues. There is a likelihood function for this, involving, not surprisingly, Krauss operators, given the composite nature of it. And there is a filtering as well that comes out of it. Okay, so there are a number of papers recently that have shown that a few features of classical Markov models, and I'm running out of time, versus quantum ones. The one that is most relevant for what I'm talking about, because we're extending it, is a paper by people from Wells Fargo, actually. And they show that a quantum hidden Markov model with NQ hidden states, has rank n squared q. So that's the quadratic sort of dimensionality reduction that I mentioned earlier. Now, the extension of it is that we are looking at a misspecified model. So in classical statistics, that means that you're minimizing the Kullback-Leibler divergence. And related to that Kullback-Leibler divergence is a likelihood ratio between, in this case, the best model that is the star, meaning the best model that you can estimate with NQ hidden states, quantum, versus the classical one with NC hidden states. And you expect that likelihood under the true DGP to be positive, not negative. And we don't really know the distribution of that. I only know the expectation of it, because even if it's were all kind of classical, it would not necessarily be a chi-square distribution. Excuse me. Because that means there are parameters at the boundary, and it's not necessarily nested. So when you go to the econometrics literature, there are papers on that kind of will tell you that. So we kind of do a hardware implementation on a classical simulator of quantum. And there is an ansatz circuit that gets repeated for every time period. So there's 3 time periods here. And then for that ansatz circuit itself has this circuit structure. So we do, there is an issue that, given the interest of time, there's a discussion about hardware and Markov properties when you actually implemented it on actual quantum hardware. So there is a discussion of that in the paper, and you will see there's a test for Markov properties that we kind of look at in our context. So this is just a simulation evidence of that quadratic dimensionality reduction. We generate data from a Heston type, that's a CIR model that mimics the S&P 500 returns on a 500 sample of size 500. Here you're looking at a 2 hidden states Markov quantum hidden Markov model versus a non-parametric hidden Markov with 4 hidden states. That's 2 and 4. Here you've got 4 and 16. And you can see that these likelihood ratios are indeed, this is 1,000 draws, are indeed all, in the positive domain, and therefore the expectation is non-negative. There's some negative outcomes here, but the expectation is definitely positive. And this is the last case is actually for hidden Markov in the quantum with a parametric, correctly specified, well, it's not correct, it's still approximate, but it uses the CIR exact discretization, and you still have the quantum advantage, apparently, which we thought was interesting to observe. I am not going to, or I'm running over time, definitely. So there, the last part in the paper is non-asymptotic bounds. I mentioned earlier, Spokorny has this work. These are non-asymptotic bounds, in this case on the filtering, not on the parameter space. There's nice work by Luc Le Hérissi that we kind of generalize, and I'm not going to be, so you get tighter bounds basically, thanks to the quantum. I wanted to thank you with that slide. Just this funny way to end my talk. Thank you. I hope I didn't abuse too much the extra time I used.
Thank you very much, Dr. Ghysels. Thank you. Are there some questions from the audience, please? Yes, please. Also say who you are.
Hi, Professor Ghysels. So I'm Carl Locke from UC Santa Barbara. Okay, so I have a question regarding your quantum Markov model. I just want to know, like in your volatility model, when you are using the quantum hidden Markov model, are you assuming the volatility model is still the classical SDE model, or you are using some quantum dynamics? And also, when you are using quantum hidden Markov model, are you assuming the hidden Markov chain is some kind of invariance, or like just a usual classical process? Thank you.
That's a very good question, actually. So yes, I'm still using the classical because I'm comparing it with how much the classical model approximation, likelihood function approximation behaves. But you're absolutely right that once you're talking about quantum hidden Markov models, you can kind of expand the realm of models that you look at. And there's sort of recent work that notably has used quantum walks to sort of model stock returns. That's not for the volatility process, but for the return process. But you're absolutely right that it also kind of opens the door to more general processes. So it's a very good comment. Thank you.
Thank you so much. Yes. And so by the way, I'm actually working under like Professor Fook, JP Fook. So Professor asked me to say hi to you.